Hello, hope everyone is doing fine. Today we're going to keep on talking about the Z transform. Specifically, we're going to talk about some of the properties of the Z transform. So we've talked about the transform, the inverse Z transform. Let's look at some of the properties. Remember when we were looking at the discrete time Fourier transform, we looked at some of the properties. It's basically the same thing here. There are a lot of properties of the Z transform. They're in the book. Please go and look at it. Go over them. We're going to go over just a couple, some that I think are most useful to us here. So let's start out. Let's say we have a sequence, G of n, and that sequence has a Z transform. Let's call it G of Z. And let's call the region of convergence of G of n or G of Z R of G. The first property we're going to look at is time shifting. In other words, if we take a sequence and we shift it in time, what happens to its transform? Turns out that if we shift it by n0, in this case, we shift it to the right by n0. In the Z transform domain, we have to multiply by Z to the minus n0. Now, the region of convergence is going to be the same as it was before, except since we're multiplying by Z to the n0, 0 and infinity could change, or the region of convergence at 0 and infinity could change. Let's see how we can use this. Now, some of the properties I'm going to prove, some I'm not going to prove. You can prove them. But all of these properties are very useful when we're trying to calculate the Z transform of other sequences. Now, we know what the Z transform is of certain sequences. Now, let's say, for example, that they give us this x of z with this region of convergence, and they say, find the inverse Z transform. Now, we look at this, we can leave it like this or convert it to negative powers of z. Maybe if we convert it to negative powers of z, it'll be more obvious. So if we multiply numerator and denominator by z to the minus 1, we get this. And if we factor out this z to the minus 1, we have this multiplied by this. Now this is exactly of the form that we have up here. We have a g of z multiplied by z to some power. So then this part would be our g of z, and this would be n of 0. This would be the shift. Now we know what the inverse transform of this part is, right? It would be 1/4 to the n times the step function. Now since it's multiplied by z to the minus 1, it's shifted by 1. Instead of being 1/4 n mu to the n, we get 1/4 n minus 1 and mu to the n minus 1. So this is really useful if we have extra z's, or if we need a z, we can always add it or take it away using the shifting property. We can also use it, for example, in the transform of the impulse function. As you know, the impulse of delta of n is 1. The region of convergence is all values of z. Now, what would the Z transform of delta of n minus 1 be? Now, using the shifting property, we just get z to the minus 1. Of course, since we have 1 over z, or z to the minus 1, the region of convergence is not all z anymore. It can include the value z equal to 0. The next property we're going to look at is differentiation. Now, this is not differentiation in time because, of course, g of n is not a continuous function, it's a discrete function. But what happens if we take the derivative of the Z transform and then multiply it by z to the minus n? Turns out we get the same sequence as before, but multiplied by n. This one we are going to prove. Now, let's start out with the general definition of a Z transform. G of n. This is the Z transform to find out g of z. So let's take the derivative of each side. Let's take the derivative here with respect to z. Take the derivative here with respect to z. Now, both the derivative and summations are linear processes, so we can interchange the order. And since we're taking the derivative with respect to z, this is the value we'd get here. Everything stays the same except this value, which becomes minus n. Z to the minus n plus 1. Now we can factor out this negative value in the z to the minus 1. And inside here we get n g of n times z to the minus n. And so if we take this to the other side, then we'd get z times this derivative, and this is what we'd have here. Of course, by definition, this is the z transform of whatever is multiplied by z to the minus n. So this is the z transform of n times g to the n. How is this useful? Well, if you remember back when we were doing inverse z transforms, one of the inverses I just gave you and I said we'd prove this later, well, now we're going to prove it. We know that a to the n mu of n has a z transform that's 1 over 1 minus a to the z to the minus 1 with a region of convergence that's magnitude of z greater than the magnitude of a. Now, if I multiply this by n in time, in the Laplace transform I have to multiply by minus z and take the derivative. Let me convert this to positive powers of z just to make it easier. And if we go through the procedure, we get this, which is the z transform that we had talked about. So if I have a sequence n, a to the n mu of n, this is going to be its region of convergence, it's going to be its z transform, where the region of convergence is the magnitude of z greater than the magnitude of a. Another property that's extremely useful to us is the convolution property. This is very similar to when we were using Fourier transforms, but actually we use it even more. And we need to prove, what we want to use, is that if we have two sequences in time, and if we take the convolution of those two sequences in time, it turns out that in the Laplace transform domain, we do a multiplication. Now the region of convergence in this case is not as clear as in the other cases. All we can say is that the region of convergence of the multiplication includes the intersection of the regions of convergence. And the problem here is that x of z and y of z both can be polynomials. Now, if there are no cancellations of poles and zeros, then the region of convergence is going to be the intersection of the regions of convergence. However, in some cases, we could have a 0 of x cancel a pole of y, and the region of convergence could change. So let's go through the proof quickly. It's very similar to the one we did before, but let's go through it again. Let's take the z transform of the convolution. So by definition, we write the summation and we multiply it by z to the minus n. Now then we write out what the convolution is, and then we have two infinite summations. Now we know that the z transform is a power series, and we're going to assume that the z transform exists. And so in other words, remember when we began talking about z transform, we said the transform existed if the sum of the magnitudes was less than infinity. So that means this power series is going to converge absolutely. Converge absolutely means that the sum of the absolute values converges. And so it converges uniformly in its radius of convergence. In other words, this is just a long way of saying that if the z transform exists, we can interchange the order of the summation of n and the summation of k. So that's what I'm going to do here. And once we do that, we take out everything that doesn't have n, and we leave this part. We also add a z to the k and a z to the minus k. In this part here is just going to be the z transform of y. Once we take that out, all that's left is the z transform of x. And so we see that a convolution in time is a multiplication in frequency, or in Laplace. The homework problem that has a little bit to do with this is number 6.27.